As a first example of a change in a natural system, I'd like to cover the process of eutrophication, specifically because it's an example where we can see our aquatic ecosystems change from a state that we tend to find very desirable, which is with clear water, right, and not a lot of phytoplankton and that type of, and high oxygen levels for fish, to a state that we find unappealing, right, which is to have very high levels of algae growth and to have dead fish kind of coming up on the shore and things like that. So we're going to look into how that happens. So first of all, to define our terms. So when we're talking about eutrophication of aquatic systems, we're talking about what happens in our freshwater and marine ecosystems when they get very high levels of nutrients coming into these. And we'll see that these nutrients can be grouped into two big categories, those that are reactive forms of nitrogen, and then also phosphorus. And when you have eutrophication occur, what happens is you get an aquatic community that becomes dominated by phytoplankton. We measure that by looking at a little bit of water and seeing how much chlorophyll A is in it, so that's a pretty easy thing to do with absorption. And the other thing that happens when we get these high phytoplankton communities is our oxygen levels plummet, and we'll look at why that happens. Why is this an undesirable state to go from this clear water, low phytoplankton system to very turbid water, high phytoplankton? Well, in some cases, it can actually have a negative impact on the water supply and make it, depending on what type of bloom you get in your plankton community, you can sometimes have toxins in the water that create a water crisis situation because it's affecting people's water supply. So this is just some news articles associated with that, like this New York Times article from 2014 when this eutrophication event happened in Lake Erie and affected Toledo's water supply. If we think about our marine systems, we have eutrophication events that create these low oxygen zones down in the Gulf of Mexico, and these can be very large, to getting to the size of even whole states. Part of why I'd like to cover this process early is this is a growing problem. And in this pattern here, we can see the global patterns of reactive nitrogen, both historically and then projected. And so what you can see is the historic low levels of nitrogen in our marine systems and our terrestrial systems, and then the projected, these very high levels. And I want you to ask yourself a question, right? So we've talked about how reactive nitrogen is one of the groups of nutrients that can cause these eutrophication events. So I want you to try to think back to chemistry, or maybe you're in chemistry right now, and think about, okay, what do we mean when we talk about reactive nitrogen? And then maybe it will help you figure out the answer to this question to also think about what is an unreactive form of nitrogen and where do we find it. So take a deep breath, and yes, that is a clue, and think about that question, and when you're ready, we'll go on to the next slide. So this is one of our biogeochemical cycles. This is our nitrogen cycle. As you can see, it's pretty complicated. And the other thing that you can see in here is that we've really modified it. The ways in which we as humans have modified the nitrogen cycle are shown in the yellow arrows here. And what I'd like you to pay attention to right now is just the atmospheric component of the nitrogen cycle, because it'll help us orient when we start to think about what we mean by reactive versus unreactive nitrogen. So the first thing I want you to see is that huge amount of nitrogen in the atmosphere. So the nitrogen cycle is known as an atmospheric cycle because there's so much nitrogen in the air. And that's why I ask you to take a deep breath, right? Because you'll be like, oh yeah, I'm breathing in mainly nitrogen, right? So 78% of the atmosphere, you can see there's a huge pool of nitrogen there, but it's in that form into nitrogen gas that's very inert. The reason why is those two nitrogen atoms are held together with a triple bond that's really, really hard to break. So you have this big pool of atmospheric nitrogen. It's very inaccessible. It's a very inert form. Then you can see if you go just one box down in the nitrogen cycle, one thing that we have done, we have these yellow arrows feeding into that box where it says reactive nitrogen. And then it has some of our various forms of reactive nitrogen listed, right? Like our nitrous oxide and our ammonia. And then, of course, we could also think of our nitrates and our nitrites and our ammonia, ammonium, all of those. So basically, all of these forms where you attach either some variety of oxygens to it or some variety of hydrogens. So you can start to see why we also have the term reactive nitrogen, right? Because once we move from that inert form, it can actually have a lot of different forms that are reactive. So we've clearly made more reactive nitrogen in the atmosphere. The other thing you'll see on here is a yellow arrow coming down from the atmosphere that says industrial nitrogen fixation. So what we're doing there is we're making fertilizer, right? So we pull that nitrogen out of the air, we combine it with hydrogen gas, high temperature, high pressure, and we make reactive forms of nitrogen that we put out on our fields. All of us are familiar with the big white tanks out on the cornfields here in Illinois. Well, it turns out those big white tanks out on the cornfields impact our stream systems and our ocean systems. So this is looking in particular at first nitrogen and then phosphorus, and where are they coming from before they hit the Chesapeake Bay on the East Coast. And so you can see that fertilizer for agriculture is a big piece of where those increase in nutrients to our aquatic systems is coming from. And you'll see that for nitrogen in particular, we already talked about how we create more reactive nitrogen in the atmosphere. So you can see that big green slice to the pie too, suggesting that another big source of nitrogen for the bay is that atmospheric deposition. I will say that burning fossil fuels is one of the things that creates that. So we have a variety of sources in our landscape, and because of how we modify things with fossil fuel use and fertilizer use, that make it so that there's more reactive nitrogen and more phosphorus coming into our waterways. So what then happens ecologically when we get nitrogen or phosphorus coming in to a system? Well, here we have freshwater river coming into a lake or an ocean. And the first thing that happens is you get that bloom in the phytoplankton. So it makes sense that because nitrogen and phosphorus, they're basically like plant fertilizers, right? So when you increase the amount of them in your lake, all of the phytoplankton will flourish. What that means is that you'll get a big buildup of that algae, if you will. And as that biomass increases, you also have a lot more dead algae, right? And that will float down to the bottom of your lake. As that biomass accumulates, you start to have what's called a high demand for oxygen in the system. And that's because your decomposers are going to be consuming oxygen as they break down all of that dead organic matter that's being produced by the phytoplankton. At some point, that oxygen demand can become so high that you don't have enough oxygen in the system to support your species that need higher oxygen levels, right? So this could be your fish or your shrimp, if you're in the marine system, and then you get these low oxygen conditions, and then your fish and your shrimp and your other invertebrates start dying. Now you've got even more dead organic matter, and you end up with an ecosystem that's very high in phytoplankton, very high in dead organic matter, very high in decomposers, and very low in oxygen. These are what are called the dead zones. It's a little bit of a misnomer because it's not as if things aren't living there, but the things we like don't do very well there, right? Like our beautiful fish and our shrimp don't do very well there. So we think of them as, or we call them dead zones. And unfortunately, since all of these processes that create more reactive nitrogen are increasing in the landscape, right, we now have more and more dead zones occurring globally, and associated with that, the low levels of oxygen and these die-off events. And so you can actually have anoxic conditions, right, or even hypoxic conditions. Now, why are these two groups? Why did we talk about both phosphorus and reactive nitrogen? It's important to think of those two as separate, even though the process of eutrophication overall is the same, because they tend to be different in terms of the systems that are impacted. So in freshwater systems, they tend to be phosphorus limited, and we'll talk a lot more about this in this class, but the main thing that it means is that, hey, if I want a lot more algae to grow in my lake, if I add phosphorus, a lot more algae will grow. So it is the nutrient that tends to limit phytoplankton growth, population growth. So phosphorus tends to be the limiting nutrient in freshwater systems, as opposed to our saltwater systems. Our marine system tends to be our reactive nitrogen. That's why what we do here in Illinois, right, when we put nitrogen on our fields and then it ends up in our streams, in our lakes, eventually it gets down, some of it, to the Gulf of Mexico, and when it hits that marine system, it will cause that eutrophication event that causes the Gulf of Mexico dead zone. Okay, so let's take a step back and see if we can answer a question based on what we've just learned about eutrophication. So a little bit closer to home, we want to go and study Lake Springfield because, you know, it's nice to be out on our boat and take a water sample. So we do that, and we're doing that over time. And as we get these water samples, we measure two different things in them. One is we're looking at absorption for chlorophyll A, and then we're also measuring the phosphorus levels in the water. And so I have a lot of different data points. So going in, I'm going to make a hypothesis as to what relationship I expect to see between the phosphorus level in the lake and the chlorophyll A excuse me, concentration. So which of these do you think is correct? Do you think you would find a negative relationship between X and Y, positive, or really no relationship? And one thing, I put it at the very beginning, what chlorophyll A measures. So think about what would have chlorophyll in the lake, right? And that will help you figure that piece out. Pause it, see if you can come up with an answer, and then we'll talk about it in the next slide. So hopefully you answered, oh, it's going to be a positive relationship, right? Because as we have more and more phosphorus coming into this lake, you'll have more and more phytoplankton growing. I can measure my phytoplankton by seeing how much chlorophyll A is in my water, and so I should see a positive relationship. Okay, this is just showing you that yes, we do actually see positive relationships between, on the x-axis here, phosphorus input rate, and on the y-axis here, the average level of chlorophyll A. Again, that's measuring the phytoplankton levels. Now, this isn't data from Lake Springfield. What this is actually is from a cross study of a lot of different lakes, some lakes that have much higher phosphorus inputs than other lakes, right? And so what we can see is as you have those higher phosphorus levels in the lake, they're positively associated with higher levels of phytoplankton. Okay, that's it. Hope you understand eutrophication now.